All right. Yeah, thank you very much for the introduction. Today I'll be talking about a Chern-Calabi flow on Hermitian manifolds. So here is the overall structure of the talk today. I'm going to cover some background, focus, define some basic quantities, and then move into talking about in the Keller setting, the Calabi flow, which is the gradient flow of the Bott-Chern energy. And then from there, we'll talk about the convergence of the Calabi flow. And after that, we're going to see how this theory can be generalized to the non-Keller setting. So here we're going to be working on compact complex manifolds still, but we no longer require that the metric be closed. So we're loosening the Keller condition. And here we can still define an analog of the Calabi flow. So here we call it a Chern-Calabi flow or Hermitian metrics. And then to show convergence of this flow, we'll need certain estimates. And so I'll go over an outline for those estimates. So here's the basic setting. So you let X be Xj omega be a compact complex manifold of complex dimension n. J is a compatible integral complex structure, and omega is a Hermitian metric on X. And so omega is this real 1-1 form we can write locally as the sum of Gij bar, dzi wedge dzj bar, where we've chosen these local complex coordinates zi through zn, zi bar, sorry, z1 bar through zn bar, etc. And here Gij bar is a positive definite Hermitian matrix. So the resulting thing is a nice Hermitian metric on X. And so, like I mentioned, if this 1-1 form is closed, so if d omega is 0, then we say that this metric omega is Keller. So in the first half of the talk, we're going to be working in the Keller setting. So we're going to assume that this metric is closed. Once you assume it is closed, you get very nice symmetry properties. In the absence of this, if you assume that it's no longer closed, you lose a lot of the symmetry. We'll see that presents, it causes some minor problems, but we can really tweak them and still find analogs in the more general setting where we assume that omega is not closed. Okay, so here we're going to define a few curvatures. So firstly, the Chern-Ricci form or Chern-Ricci curvature is a 1-1 form given by negative dd bar log determinant of the metric G. So I use the word metric to describe both G as well as omega. And then here, the first Chern class is the Dolbeault homology class of this Chern-Ricci form. And so if you trace this Chern-Ricci form, then we get this quantity, the scalar quantity, which we'll call this Chern scalar curvature. Right, so the Ricci is a 1-1 form. Once you trace it with omega, which is another 1-1 form, you're left with a scalar quantity. And when the metric is Keller, then if you define both the Chern and Levi-Civita connections in that instance where omega is Keller, the respective connections agree. And so in the Keller setting, you basically have one Ricci curvature and one scalar curvature. But when you work away from the Keller setting, depending on how you trace the full curvature tensor, you can get 4 different Ricci curvatures and 2 different scalar curvatures. Yeah, depending on the order in which you trace the indices. Okay. And so Calabi, so this is now all in the Keller setting for now, was trying to define canonical metrics within a Keller class of a metric. So the Keller class of a metric is the dd. So in the Keller setting, you have the dd bar lemma. So then you can talk about the dd bar class of a metric. And so he was trying to define within a given Keller class. So given a metric omega, up to addition of dd bar of some smooth function phi, when is this resultant metric, which we can call omega phi, canonical in some sense? And so the way that he first introduced it was he defined this Calabi functional. So it takes in a metric omega, and it's effectively the square of the L2 norm of the scalar curvature. And so the square of the L2 norm can be broken down into the sum of these 2 integrals, where the first one is now normalized to be the L2 norm of the scalar curvature minus the average scalar curvature on the manifold. And the second term is just this extra correction term, which is just the L2 norm of the scalar curvature on the manifold. So again, this underline R is the average scalar curvature. So it's defined as integrating all of the scalar curvature on the manifold and dividing by the volume. And then you can break this out and see that in fact this quantity is invariant within the Keller class or cohomology class of omega and the first, or it depends on, the Keller class of omega as well as the first Chern class. but doesn't depend on phi or, you know, however you're moving within that class. It's an invariant of the Keller class of omega. Okay, and so Calabi defined extremal metrics to be critical points of this functional, which we call the Calabi functional. And then from this second equality here, we can see that CSCK metric, which are constant scalar curvature Keller metrics, which are those that satisfy that. So if your scalar curvature is constant everywhere, then you're going to be equal to your average scalar curvature everywhere, right? And so in that case, this first term, this first integral vanishes. And since the second term is a cohomological invariant, you can see that these CSCK metrics will in fact minimize the Calabi functional within their Keller class. Because, you know, this can't be helped, this can't be changed. This is the part that you can control. The smallest that this can be is 0. And that's exactly when R of omega is equal to underline R everywhere on X, right? Chen and I think, yeah, there was further work later on to show that in fact, in the absence of CSCK metrics, external metrics are also minimizers of the Calabi functional, but that statement takes a lot more work to prove. It's not as immediate as the statements I've made here, which you can read off pretty straightforwardly from this equality above. Yeah. Okay, so we're gonna briefly describe some examples of CSCK metrics. So the best known examples of CSCK metrics are Keller-Einstein metrics. These ones have gotten probably the most attention of all of them. And these are the ones that satisfy that the Ricci of the metric be equal to some scaled version of the metric itself. So we can write it as lambda omega. And so up to scaling, so when you scale the metric, it doesn't change the Ricci, but it's going to change the right-hand side. And so really you only have to consider the 3 cases on like the sign basically. So it's like either lambda is the negative case, in which case we can just assume that it's -1, or it's the 0 case, or it's the positive case, in which case we'll just let lambda be +1, just to work with nice numbers here. And so in this first case, when lambda is 1, classic example of this would be the Fubini-CD metric on complex projective space. And then for lambda equals 0, this gives you the family of Calabi-Yau metrics. And then for lambda equals -1, an example would be the hyperbolic metric on Riemann surfaces of genus greater than or equal to 2. And so like I mentioned, Keller-Einstein metrics are a specific case of CSCK metrics, and CSCK metrics are a specific case of extremal metrics. Since these are minimizers of the Calabi functional, and extremal metrics are all critical points of the Calabi functional. In certain instances, these things are actually equivalent. So if like the first Chern class is signed, so it's positive, negative, or 0, then all CSCK metrics on that manifold are going to be Keller-Einstein. Similarly, if you're working within a Keller class where the Futaki invariant vanishes, I think, then you in fact get that all external metrics there are going to have to be CSCK. And Yau showed a few cases. Oben and Yau showed the case where C1 of X is negative. But here I'm going to just make the statement for the Calabi-Yau case because it's going to be more relevant to us later in this talk. So when the manifold is Calabi-Yau, that is when the first Chern class vanishes, there exists a unique Ricci flat metric in any given Keller class. So this is an important statement. So it's like given any Keller metric omega on your manifold X, satisfying that the first Chern class of X is 0, you can always find some phi for which omega plus dd bar phi, that resultant metric is Ricci flat. And it'll be the only Ricci flat metric differing from the original given metric by addition of dd bar of some smooth function phi. So unique within that Keller class. Okay. And so recently there's been progress. So now I'm shifting back to the CSCK case. So CSCK in general is, you know, when the first Chern class is not positive, negative, or 0, they're more general than the Keller-Einstein metrics. And so there's been recent progress into proving existence of these metrics. And so the Keller-Einstein case, which was resolved by Oben and Yau, is clearly a very substantial and notable problem that they solved, but the equation there is second order, which means it's a little bit easier to work with than the CSCK equation, because the CSCK equation now is fourth order. Because the CSCK metric, you're tracing over the Ricci. There's more going on. It ends up being a fourth order PDE. And so the trick that Chen and Chang used in their recent work to show existence was to then break down the fourth order PDE into a pair of second order PDEs. So in this case, you can break it down in 2 steps. You can first define this function f to be log of this ratio of volume forms, omega phi to the n over omega to the n. And then taking its Laplacian now, with respect to the metric omega phi of f, you impose the constant scalar curvature part now, because the first term that comes out is going to be negative r, like r sub phi, which then if you require to be negative underline r is going to, that's imposing the CSEK condition. And then the second term that pops out, because you're tracing with respect to omega phi, the second term doesn't simplify as nicely. It remains this trace omega phi of Ricci of omega. Since these 2 metrics are now different, this is as far as we can reduce the statement. It doesn't collapse further into someone's, full scalar curvature. Okay, and so what they showed was that, so in general, CSEK metrics may not always exist. There's lots of examples on manifolds where they just don't exist. And so of course you can't prove existence all the time. The condition that they used here is that you can prove these a priori estimates, which inevitably then will provide you with the necessary tools you need to show existence, dependent on the fact that you need to have bounded entropy. And so this bounded entropy quantity, or this entropy quantity, is defined as the integral of log omega phi to the n over omega to the n integrated with respect to omega phi to the n, right? So the condition is that if you have bounded entropy, then we can obtain these a priori estimates from which we can prove closeness, openness, et cetera, like using this continuity path that I think maybe we'll get into after. And so the statement that Chen proved, which is the biggest breakthroughs, are these a priori estimates. And so they state that if x omega phi is a CSEK metric, where omega phi, differs from omega by addition of dd bar phi for some smooth function phi, then we get that the CK norm of phi of all orders k is going to be bounded by some constant depending only on k x omega and this entropy quantity. Okay, and so they use their estimates to prove then, ignore this typo, that properness of the Mabuchi energy in terms of the L1 geodesic distance in the space of Keller potentials, in fact, implies the existence of a CSEK metric. So the statement here, the original statement here is like a geometric version of the entropy bound. And so we know then once you have the entropy bound, that's going to give us the estimates. And with the estimates, you can show existence of a CSEK metric. And so that's the direction that they showed. The previous direction was shown in 2016 by Berman, Darvash, and Liu. So they showed that in the opposite direction, if you know that there exists a CSEK metric, then you can show properness of the Mabuchi energy in that sense. Okay. So before we, so one thing to consider here is that other ways of seeing when a metric does not exist is the Spooky invariant that I'll get into. And so this provides, it's like the classic example of an obstruction to existence of a CSEK metric. So if we let, again, R underline R be this average scalar curvature quantity, then because we know that, by definition, it's going to integrate to R minus underline R is going to integrate to 0, there's going to be some H for which Laplacian of H is going to equal to R minus underline R. And so Futaki showed in 83 that you can define this invariant for the Keller class omega, which we call f of v, where you feed into it a holomorphic vector field of the form vi equaling gij bar, dj bar of f. So when you feed into it this type of holomorphic vector field, the quantity is defined as negative of this vector field on H, integrate against omega to the n. And then by straightforward integration by parts, which you can do very nicely in the Keller setting, this integral becomes just R minus underline R against this little f. So this f is like the holomorphic potential for this holomorphic vector field V. And so it can be shown using, a relatively short computation that f of v is an invariant on the Keller class. So it doesn't matter which metric you choose in particular inside the Keller class, but as long as it's inside this Keller class, f of v will be the same quantity. And so from here, you can see that if f of v does not vanish for some holomorphic vector field v, then there cannot exist a CSEK metric in that Keller class, because if that Keller class had permitted a CSEK metric, for that particular CSEK metric, R minus underline R would be 0. And since that's an invariant of the class, it would have to be 0 for all V. So basically, the obstruction here is if you can find, if given some manifold and some Keller class, you can find some V for which this f of V is not 0, then you can conclude that in that Keller class, there is no CSEK metric. Yeah. Okay. So another approach to the CSEK problem is the variational approach introduced by Mabuchi. So here, if we let x omega naught be a compact Keller manifold, so I'm just changing notation slightly here. We define omega t to be omega naught plus dd bar phi t. Then the Mabuchi energy in its variational form is given by ddt of Mabuchi, starting at omega naught of omega t will equal to this negative of this integral here, where here we have the time derivative on phi, and then here we have r phi minus underline r omega t to the n. And so you can see from this definition that fixed points or stationary points of Mabuchi energy are going to give you CSEK metrics. And if you want to, if you want to do another computation that's relatively involved, you can find that the non-variational form of the Mabuchi energy can be written out as the sum of a bunch of these integrals. The first term here is actually quite nice. It looks like the integral of our entropy quantity. This is not surprising because they're all related to the existence of CSEK, so they're all kind of originating from the same place. And then you have these correction terms effectively that you'll need to add in, because when you integrate by parts out, you get a bunch of these weird terms. And so in order for to really get equality, then you have these other two parts of the Mabuchi energy when it's defined this way and it's not variational form. And here, this capital V is just the integral of the volume. So again, this quantity V is an invariant of the Keller class. Because you add dd bar phi to the n to this, you'll see that in the expansion, all the other things are exact and will integrate to 0. Yeah, maybe with some integration by parts involved. So now I'm going to talk about the Calabi flow. So again, if we let x omega naught be a compact Keller manifold, the Calabi flow is defined as it's the gradient flow of the Mabuchi energy that we just saw. And so its evolution equation, if you're starting the flow from an initial metric omega naught, which is Keller, the flow is defined by evolving the metric omega in time by a negative by dd bar of the scalar curvature. Where again, here now I'm just saying that at time 0, we're starting from this initial metric, which is Keller. And so you can see from this that this flow doesn't change the dd bar class of the metric, right? Because if you took ddt of dd bar, you'll see that, you can just put a single d here. You'll see that because there's a bunch of d's here already, it's not going to change the Keller class of the evolving metric. So the evolving metric is staying in the same Keller class. And so because that is the case, we can then rewrite the flow in terms of its evolution just on the potential function, right? Since it's not changing the Keller class, we can always write, it's staying within dd bar of something of this omega naught. So we can then rewrite the flow in terms of evolving this phi of t quantity instead, which is easy to work with because phi of t is just some smooth real function. And so phi is normalized so that, so I guess, phi is not unique unless you normalize it. So you can either normalize it so the sup is 0, or you can normalize it so in this case that the integral is 0 over your manifold. And that's just to ensure that it's unique. And then from there, you can rewrite the Calabi flow in terms of this evolution equation on phi. So this same flow then is equivalent to evolving phi. The ddt of phi is just going to be the scalar curvature minus the average scalar curvature, where now you can assume that phi at 0 is just 0. Right. And we can see from this that it's the gradient flow of the Mabuchi energy, because if you take the time derivative of the Mabuchi energy, recall from the previous equation, for the phi dot part, we're just plugging in this right-hand side. And so when you plug in this right-hand side, you just get negative of this L2 norm, which is clearly going to be non-positive, be less than or equal to 0. Yeah. And so you can also see from this, I guess, more directly that these fixed points are CSCK metrics, right? This L2 norming 0 requires that this inside part be 0. Yeah. Okay. So what do we know about the convergence of the Calabi flow? Well, firstly, Chen, he proved short-term existence of the Calabi flow and global existence of the flow under the assumption of a uniform Ricci bound. So again, this flow is more complicated than the analogs in the Keller-Einstein case. In the Keller-Einstein case, one of the flows that people work with is the Keller-Ricci flow, which is a second order flow whose fixed points, if you normalize a certain way, are going to give you the Keller-Einstein metrics. But since this flow is dealing with constant scalar curvature metrics, this is a fourth order flow. And so a lot of these, even though it's parabolic, a lot of these basic properties are a bit more difficult to show than they were in the Keller-Einstein case. And so they also show global existence of the flow under the assumption of a uniform Ricci bound. And then Zicklahidi proved that uniformly bounded curvature along the flow and proper Mabuchi energy implies that the flow converges to a CSCK metric. So it's providing conditions on which then, if starting from some initial metric, the flow converges to the desired CSCK metric. And then finally, Chen's son proved that if the initial metric is sufficiently close to a CSCK metric, right, then you would hope, if the flow is reasonable, that it would then exist and converge to that, which in fact is what they show. So then they show that the flow exists and converges uniformly to that specific CSCK metric. So you have to start close to it and obviously be in the correct Keller class. Okay, so now the question from here is, taking this theory from the Keller setting, how much of it can we extend to this more general non-Keller setting? And so now working still with compact complex manifolds with complex integral structure, complex structure, but no longer requiring that this metric that we're working with omega is closed. Okay, so let's just, so here's some just general information about like what's known about constant Chern scalar curvature metrics. Okay, so like I alluded to earlier, in the non-Keller setting, there are two different scalar curvatures that you could consider. And the one that we'll be focusing on is this Chern scalar curvature, which arises as a trace of the Chern-Ricci curvature. And so this one, for now, so I mean, there's research in studying both of these different scalar curvatures that arise in the non-Keller setting. But this one works more naturally as an analog in this case because the Chern-Ricci curvature is more natural to work with because it's a real 1-1 form versus the other Ricci curvatures no longer retain that property. And so then the theory becomes very different in that case. So we're going to focus specifically now on Chern scalar, like constant Chern scalar curvature metrics. And so firstly, so the classical Yamabe problem has also been generalized to this Hermitian setting, which they've now called the Chern-Yamabe problem. And so they show in this setting that the existence of a constant Chern scalar curvature metric within a given Hermitian conformal class. And this was shown by Angela, Kellermeyer, and Spotty in 2017. And they show existence in the case where the expected constant Chern scalar curvature is non-positive. And then Koka and Lejmi in 2019 explicitly constructed constant Chern scalar curvature metrics on ruled surfaces. Yeah, so I think it was like on, here's a picture with a non-zero degree that are known to not admit any CSCK metrics. So it's still Keller manifold. You can in fact show that, well, they've explicitly constructed some constant Chern scalar curvature like non-Keller metric. Yeah. Okay. So I'm going to focus on the case now where the first Bott-Chern class of the non-Keller manifold that we're considering is going to vanish. And so this is a more restrictive condition than just being Calabi-Yau in the sense that the first Chern class vanishes. And so the Bott-Chern cohomology is defined such that H11 of Bott-Chern is just declosed real 1-1 forms over DD bar exact things. So do things of the form DD bar psi for some smooth function psi. And so for non-Keller manifolds, the condition that the first Bott-Chern class vanishes is stricter than just having your first Chern class vanishing. And so, for example, the Hopf surface, which we know is diffeomorphic to S1 cross S3, clearly has like 0 second, like B2 is 0. So C1 of X is going to be 0. But it satisfies that, in fact, it has a metric on it for which Ricci of that metric is always, Chern-Ricci of that metric is always greater than or equal to 0. So it doesn't satisfy that the first Bott-Chern class is going to vanish, right? So that's an instance where it's Calabi out in the sense that its first Chern class vanishes, but it's not satisfying the vanishing of the first Bott-Chern class. And in this setting, it was shown by Charrier and Tossetti-Weinkow that when a manifold has vanishing first Bott-Chern class, there exists a unique Chern-Ricci flat metric in any given DD bar class of a Hermitian metric, right? So now we don't have Keller classes anymore because we don't have closeness of the metric that we're working with. But we can still ask this parallel question of like existence of some sort of, canonical metric in the sense lying within the DD bar class of the given Hermitian metric. Yes, and so this fact is going to be like is a motivating piece for why we then can define this Chern-Calabi flow, and it's going to provide us with the fixed points for this Chern-Calabi flow. Okay, so the Bott-Chern energy, it turns out, can also be generalized to the Hermitian setting, but only in the case, not only, but like is only, makes sense so far. We've only studied the case where the first Bott-Chern class vanishes. Studying the Bott-Chern energy in the more general setting of non-Keller manifolds without requiring this condition that the first Bott-Chern class vanishes is just a bit trickier, because in the definition of the Bott-Chern energy, if we go back a few times, it's the two extra ugly terms basically both depend on underline R. So if underline R is 0, then you lose all those extra integrals, those two sums of extra integrals. And if you don't have underline R vanishing, then so effectively this all reduces to the problem that like integration by parts behaves very poorly in the non-Keller setting. And so things can go wrong. Like things easily go wrong when you have to integrate by parts. So far, it only seems the integration by parts seems to only work out when we work in this very nice setting where the first Bott-Chern class is 0. Okay, so here the definition of Bott-Chern energy can just be written as this first integral, which is kind of just like the entropy quantity, minus this F, where F is the Chern-Ricci potential of the metric, of the initial metric omega naught, and then with this other correction term, which only depends on F and omega naught. So it only depends on omega naught, effectively. And here we normalize accordingly and find that in this case, if omega naught is Keller, then this Bott-Chern energy, of course, this quantity that we've defined here agrees with the standard Bott-Chern energy in the Keller setting. Hence the naming it still the Bott-Chern energy. But in this quantity now, in fact, also works for non-Keller metrics. And we can see here then that critical points of this, generalized Bott-Chern energy to the Hermitian setting are going to give us these Chern-Ricci flat metrics. So everything just carried over where now it's non-Keller, all the Ricci flat things are now Chern-Ricci flat because we have to be more specific. And we choose a Chern-Ricci one because that's what follows most naturally, because it's going to be given by. So like working within the vanishing first Bott-Chern class is nice, because that means that, for any metric omega naught, we have that we can write Ricci of it as DD bar of some function, right? By the assumption that the first Bott-Chern class is vanishing. Okay, so again, if we work in this specific setting and we differentiate the Bott-Chern energy that we just previously defined on the last slide, then we see that it's going to be equal to log of this quantity against Laplacian of phi dot, the time derivative phi, integrated against omega phi to the n. And so you can see from this a few things. The first thing is, depending on what you choose phi dot. So yeah, the goal here is we want to find different, I guess, like flows along which the Bott-Chern energy is decreasing. So the second order one that you could see is if you took phi dot to be log of this volume ratio, then you have log of some, so you have like some function against Laplacian of that same function, then that integral can be written as negative the integral of the gradient of that function, right? And so that's me a non-increasing quantity, or rather the time derivative of Bott-Chern in this case is going to be less than or equal to 0. So in this case, this gives us the Chern-Ricci flow, because I haven't really described yet, but the Chern-Ricci flow is an analog or like, the non-Keller extension of the Keller-Ricci flow. And so both this flow again is second order, the same way that the Keller-Ricci flow is second order. From this, you can also see that, so in our case, we're considering the Sisi, or the constant Chern scalar curvature equations. If we choose phi dot to just be this whole negative of this whole Laplacian plus some torsion that arises from the integration of parts, then this flow is nice because then its time derivative is going to be negative of the L2 norm of the scalar curvature plus this correction torsion term that is not really a problem to us. So I guess I'm trying to define this flow. The important facts that we want, which maybe aren't clearly motivated yet, are we want the Mabuchi to be decreasing along the flow, because with bounded Mabuchi, we will obtain bounded entropy. And with bounded entropy, we'll show that we'll have the estimates that we want. So once you have that, you also still want to make sure that the flow that you're considering, has critical points that are of interest. So in this case, you want the critical points to be constant Chern scalar curvature metrics. Because you can probably define other exotic flows that satisfy decreasing Mabuchi, but then the critical points, I don't know, I'm not sure. They may still always be like constant Chern, but that's like another feature of the flow that you want to make sure makes sense. So with those two conditions, you find that we can define this Chern-Calabi flow. Okay, and so I guess, in order to make the integration by parts sort of manageable in the absence of the Keller condition, we do have to make this assumption that dd bar of the initial metric raised to the power of k is 0 for k equals 1 and 2. And this ensures that the integral of the volume, stays the same up to addition of dd bar of some smooth function phi. Because if these quantities kept sliding around and changing, then there's a lot more variability across all the parts of the integral or the equations that we were seeing previously. And that would just be a much, much harder problem. This also gives us that the average scalar curvature is invariant of that dd bar class of the given Hermitian metric. So again, if it kept moving with phi, if the average scalar curvature kept moving with phi, it's possible that that problem would still be interesting. It would definitely still be interesting, it would just be harder. I'm not sure exactly how much harder. And then finally, the condition also ensures that your integral of Laplacians will vanish. The integral of Laplacian of a function will vanish. And this is something, I guess, pairs with the fact that whenever we do integration by parts, we're relying on a lot of these things. And so this condition may not seem very natural, generally speaking, but it is very natural in the case of complex surfaces. Because in the case of complex surfaces, this condition reduces or coincides then with the Go-to-Shen condition, which also for complex surfaces is equivalent to the pluriclosed condition. So for complex surfaces, it's just going to become the condition that dd bar for metric omega be 0, which is still strictly weaker than the Keller condition. Okay, and so this condition that I've been referring to for higher dimensions is equivalent to saying that dd bar of omega vanishes for all the k values of interest. So 1 through n-1, because it's obviously going to vanish for all the other ones. And you can see this through a straightforward computation. You can see that dd bar omega to the k can be broken down as dd bar omega wedge some stuff, and then d bar omega wedge d omega against some stuff, where the blue terms will vanish. For this vanishes by assumption, like the pluriclosed condition. And this vanishes by the dd bar omega squared vanishing condition, because when you break this out and apply the pluriclosed condition, that forces the d omega wedge d bar omega to also vanish. So this assumption has also been used by a few, it's a natural first choice in trying to generalize to the non-Keller setting. I think it was introduced by Guan Li at some point, and has been Tosadi Weinkovich's assumption, many of the other non-Keller researchers will also use this assumption as a first pass to generalizing. Okay, and so this assumption, it might seem strong again, but in the case of complex surfaces, it's nice because it coincides with the Go-to-Shen condition. And this is nice because Go-to-Shen proved that every Hermitian metric is always conformal to some Go-to-Shen metric. So Go-to-Shen metrics always exist. Given any metric, you can make a conformal change to that metric and land at a Go-to-Shen metric. So there's like an abundance of Go-to-Shen metrics on any given manifold, complex manifold, right? So you don't have to worry about their existence. And so then if you want to see when this condition is satisfied more generally beyond just complex surfaces, the simplest example that one can come up with is if you cross this complex surface with this Go-to-Shen metric on it with a Keller surface, this resultant product manifold is non-Keller because part of it is non-Keller. Let's assume the complex surface part is strictly non-Keller. But then on this product manifold, we can find like a product metric that satisfies our condition. If you take the Go-to-Shen metric on the one part and then add it, with pullbacks to the Keller metric on the Keller part of the manifold, then this metric will satisfy the condition that we're referring to. Yeah, but all this theory that I'm working on, even just strictly working in the case of complex surfaces, is still like all very open and still very interesting. So you don't even have to necessarily consider the much higher dimensional cases of this to find lots of problems to work on. Okay, and so to prove convergence of this Chern-Calabi flow that I've introduced earlier, we'll need an analog of the Chen-Chang metric, estimates in the non-Keller setting. So the Chen-Chang estimates that I wrote earlier hold for Keller metrics, like specifically CSCK metrics. Here we show that, exactly the same statement holds for these non-Keller metrics as long as they still satisfy this condition of being pluriclosed and that omega squared is pluriclosed. And so again, because you don't have the DD bar lemma, we can still ask for the existence of a constant Chern scalar curvature differing from some given metric by addition of DD bar phi or some function phi. And then we have that if that metric is constant Chern scalar curvature, then again, we get these a priori estimates where we get that the CK norms of phi are always going to be bounded above by a constant depending on K, X, omega, and the entropy, or the entropy is defined exactly the same way. So it's really direct analog. Because we're working with the Chern-Ricci flow, these things work out very immediately. If you were to have chosen a different Ricci curvature or the other scalar curvature to work with, then the proof of these estimates would become like very different. You basically have to do them from scratch. Yeah. And from this, it follows that if you have omega phi differing from omega by DD bar phi for some smooth potential function phi, then if you now no longer assume the constant Chern scalar curvature condition, you can still get that for this phi. So this is the statement that we'll need to show convergence of the Chern-Calabi flow. You'll still get the CK norms of this phi is me bounded above by constant depending on K, X, omega, the entropy, and just the C0 norm of R phi. Yeah, so this is like all orders, and here you just need, this is the fourth order on phi basically. But then beyond that, it's just some constant depending on K. So useful estimates. Okay, and so how is the flow specifically defined? So I sort of defined it earlier where I very casually just threw everything into the torsion part. But if you wanted the explicit statement, the torsion part is specifically this giant thing here, which arises in the integration by parts. So in trying to define this flow as a gradient flow of the Hermitian analog of the Bernoulli energy, you pick up this torsion term. And so it can be shown that the fixed points, so if you're a constant Chern scalar curvature, or in this case, you're going to be, so in the setting of vanishing first Bott-Chern class, all constant Chern scalar curvature metrics are going to be Chern-Ricci flat, right? So if the metric is Chern-Ricci flat, you can see that it's going to be a stationary point of this flow. In the other direction, if this flow if phi dot is vanishing, then you can also show that this right-hand side equaling 0 will also force that the metric be Chern-Ricci flat. And that's just by undoing the same integration by parts. Like it may not be obvious that this whole thing vanishes, right? So, but it in fact is true. Like if the sum of these two things are both 0, then R of t is going to be 0, and this thing's also going to be 0. Yeah. Okay, so again, this flow agrees with the Calabi flow in the setting if omega naught is Keller. Because when omega naught is Keller, torsion is going to be 0. So in torsion 0, this whole second term disappears. you're just going to then be evolving phi of t by the scalar curvature, which is exactly what it was doing in the Keller setting, because in this setting, underline R is 0, so there's no second term here, right? And then, like I mentioned, this is the gradient flow of Bott energy. That was kind of how it was derived to be. And then fixed points are going to be constant Chern-Scalar curvature metrics, which again, in this case, are always going to be Chern-Ricci flat. Okay. And so now we can talk about convergence of this flow. So we run this flow on a compact Hermitian manifold with vanishing first Bott-Chern class, selecting an initial metric that satisfies our condition. Then we can say something about the flow. So then we can say that a solution to the Chern-Calabi flow starting at omega naught exists for as long as the Chern scalar curvature remains bounded. And this relies on the a priori estimates that I mentioned earlier. And so if the Chern scalar curvature remains uniformly bounded for all time, then we have smooth convergence of the flow to the unique Chern-Ricci flat metric in that DD bar class. So again, recall by the result by Charrier and Tossetti line code, there's always a unique Chern-Ricci flat metric inside any given DD bar class of a metric, of a given Hermitian metric. And so this flow, under the conditions where the scalar curvature is bounded along the flow, will then converge to this specific unique Chern-Ricci flat metric, which we can call omega infinity, differing from omega naught by, this DD bar phi infinity. And so, like I said, we wanted it to be a gradient flow of the Bott energy because the entropy quantity, can be bounded above by the Bott quantity plus some constant that's fixed. So if it's a gradient flow of Bott energy, then the Bott energy is not increasing along the flow, right? It can be decreasing, but it definitely bounded along the flow. And once you have bounds along the flow, then you have entropy bounds along the flow. And then once you have entropy bounds along the flow, then you have all the estimates you need to talk more about the convergence of the flow. Yeah. So that was the motivation there. Okay. And so again, you have to check that, in fact, the property that DD bar omega to the K vanishes is preserved by the flow, because you continually want to apply these estimates for the evolving metric along the flow. So for the metric to always have the estimates, for the metrics to always be able to use those estimates, the metric has to always retain that property. And so thankfully along this flow, it can be shown that the property that we need is preserved. And you can see this by taking the time derivative of DD bar. So the property is that DD bar omega to the K vanishes for all K, but like I said earlier, that's the same thing as just checking that DD bar omega is 0 and that DD bar omega squared is 0. So in this case, if you take the time derivative of DD bar omega, you find that you're DD barring some stuff with D's already in it, so it's going to be 0. And then similarly for DD bar omega squared, it breaks down into these two parts, and then this part is going to vanish. So that property is preserved, which means that the estimates that we have can be applied to the evolving metric along this flow. Yeah, so together this gives us this property is preserved along the flow. Okay, so here I'm going to outline a proof of the estimates. Do I have 5 more minutes, or how much more time do I have?
Sure, of course.
Okay, so yeah, I'm not going to go into the details of this part, but this line of reasoning follows very similarly to the method used by Chen Chang to prove these a priori estimates in the Keller setting. And so again, we can reduce this 4th order constant Chern-Scalar curvature equation, in this case, into this pair of 2nd order equations. And here we're going to be working with the Chern-Laplacian and the Chern-Ricci curvature. So everything's just the Chern parallel of what it was in the Keller setting. And so the proof method for showing these estimates, which are the crucial part of this convergence result, is to first show that you have the C0 estimates on F and phi. And then from there to show the C1 bounds on phi, followed by an LP bound on the trace of omega phi with respect to omega, dependent, for the right-hand side is dependent on p. And then from there you can do Moser iteration bootstrap and get that, obtain this L infinity estimate on this trace quantity. And so in this case, the C on the right-hand side will always depend on X, omega, and the entropy. So the dependence on the entropy gets picked up in the very first step when you're trying to show these C0 estimates. on these quantities, and then from there, like the dependence gets passed along in steps 2, 3, and 4. Yeah, and that's not surprising because these estimates should not hold generally, because we know that CSEQ metrics don't exist generally. So this is the condition that we need in this case to show the estimates work. Okay. And so once we have that, so the last thing, step 4 gave us this uniform bound on this trace. Once we have the uniform bound on this trace, we can obtain the uniform bound on the trace the other way. So now the trace of omega with respect to omega phi, and that's, you can see, it's just by the straightforward computation, you can see that inequality, you can see that it's going to be bounded above by this. And then we have this volume ratio bound is equivalent to like the C0 bound on F, because recall that F is equal to log of this volume ratio. So once you have a bound on this trace and a bound on F, then we can bound the trace the other way. And once you can bound the trace the other way, from there, you can use a bootstrapping argument using the fact that you have these two coupled second order equations to obtain all higher order estimates on phi. Yeah, using standard elliptic PD theory from there in the bootstrapping part. Okay, and so notable differences in this computation compared to the Keller setting is that, like I mentioned, when you have the Keller property, or when you're assuming your metric is Keller, all torsion vanishes. And so all your integration by parts are nice. You have closeness, you have DD bar lemma, you have a lot of tools. And when you're working in the non-Keller setting, one of the biggest problems is this torsion that arises that like no longer vanishes. And so, torsions will arise when you like commute covariant derivatives, when you try to switch indices of your curvature tensor, et cetera, as well as like when you're trying to integrate by parts. When you're trying to integrate by parts in the non-Keller setting, you get these like this red term, for instance, which you can actually also write in terms of a torsion, right? So torsion, just like these like third order annoying terms on phi. Yeah. Okay. All right. I think I'll end there because the rest of it is very technical. Yeah.
Okay. You're sure you don't want to to explain a little bit more about this C0 estimate, for instance?
I mean, I could if you guys are interested.
Yeah, I am actually.
Okay, so yeah, so here the 4 steps were the C0 estimates on F and phi, the C1 estimate on phi, the LP trace estimate, and the L infinity trace estimate. So I can quickly go through this computation. So working in the non-Keller setting, the first step is you want to find the C0 estimates. To do that, we're going to have to call on a few results in the non-Keller setting. So the first result in the non-Keller setting is a generalization of Yau's theorem to the Hermitian, like the non-Keller setting. So it's solving this complex monotone pair equation effectively. So it's saying that, like Sisi-Weinkoff showed that for every smooth real value function g on x, there exists a unique b and a unique smooth real value function psi on x, solving this PDE, this complex monotone pair equation, where you're assuming that omega plus g bar psi is always positive, and you're normalizing psi to be unique in this case, using the fact that the soup is going to be 0. And here again, we see the same condition. So here, if you assume that dd bar omega to the k vanishes for k equals 1 and 2, then you can explicitly solve for the constant b. So in this case, then b will be equal to log of this ratio, right? If you, in the absence of this assumption, you could still say that you have a solution, but then you wouldn't know what b was, and you couldn't really bound b very effectively. And so then, you're trying to obtain a C0 estimate on phi, or F in this case, phi and F. But if you don't know what b is explicitly, then the entanglement of what the dependence is might pass back to itself, and it might not make sense anymore. And that's why this assumption, this assumption was crucial for my estimate, because I was also trying to use this Sisi-Weinkoff theorem. Yeah.
So sorry to interrupt. So that's this theorem which gives the existence of the Ricci flat metric, right?
Yes, exactly. This is like the Calabi theorem for non-Keller manifolds. Yes. Okay, so once you do that, we can say that there exists that psi. So I guess, yeah, to employ the previous theorem, we're going to specify that g be equal to this thing, f log of this thing that approximates the absolute value of f. And then we're going to let psi be the solution that we know is unique and exists by the previous theorem. And then so this resulting complex Monge-Ampere equation can be written out in this way. Okay, so we'll leave it there. The next thing we'll need is the non-Keller version of Tian's alpha invariant. So Tian's alpha invariant was discovered by Tian in the Keller setting, and then many experts, I guess, like became well known that it just carries over to the non-Keller setting as well, without it really being written down explicitly anywhere. So it just says that if you have X omega, a complex manifold, there exists constants alpha and C depending only on X omega, such that for all psi that are PSH in X omega, the integral of e to the negative alpha of this normalized psi is going to be uniformly bounded above by the C. So like for this alpha and for the C, regardless of which psi you're taking inside the PSH class, this integral is always going to be bounded in this way. So it provides you with a uniform bound on the integral of this exponential of to the power of this PSH function.
But you don't need compactness?
You probably need compactness. I probably didn't write it. Yeah, probably. Yes. And so from the above theorem, we can see that for any PSH functions, this is going to be true. So then for this phi and for the psi that we're working with, these two integrals be simultaneously bounded by the same constant C and for the same number alpha. Yeah. Okay, then you do a bunch of work involving the Adp Maximum Principle. So then you define the quantity to which you'll then apply the Adp Maximum Principle, which is this thing with a bunch of free-floating constants in it to be determined as we proceed and chosen in the necessary way. And so we're going to assume that Q achieves a max at some point P, and then we'll work within this coordinate ball B of P. And so we're going to assume that theta is positive and TBD, and then define this cutoff function eta, take on values between 1 minus theta and 1, and satisfying these properties, which you can always assume your cutoff function satisfies. And then it can be shown that for lambda large enough, 2n delta lambda is going to be equal to alpha. And for theta very, very small relative to delta, we can then compute the Laplacian of Q of eta and bound it below by this quantity. So this part of the work is very involved. So I'm bypassing a bunch of steps here. But yeah, what you can see here is that it's going to, the right-hand side here depends on this integral quantity I of f, where I of f is the integral of e to the f square root of f squared plus 1. So this effectively is something that's, grows the same rate as the entropy quantity. And this is where the dependence on the entropy gets picked up. And this part is inevitable. It just arises in the way that this computation unfolds. Okay. And so from there, once you apply the Adp Maximum Principle, since you have now computed the Laplacian of the quantity Q eta, we find that the sup of Q eta on this ball is bounded by the sup on the boundary, plus the integral of the negative part of this giant thing. And so you can simplify this a little bit because you know that the square root of f squared plus 1 is positive and the integral is positive. And so the integrating the negative part here is equivalent then to integrating over the ball intersected with some set over which f is bounded from above by some constant c of this stuff. And then this stuff reduces nicely given the way that we've specifically chosen our constants, delta, lambda, epsilon. And so then it becomes, it reduces to these two guys and these two guys. This guy basically is bounded from above by the fact that we had chosen alpha to be the Tian alpha invariant. It's alpha. And so the C is the same as the C resulting from the Tian alpha invariant. And I've also relied on the fact that psi is normalized so that it's always less than or equal to 0. Yep. If you have questions about this, I can explain in much more detail. Okay. And so from this, we get that Q being bounded above is equivalent then to the exponent in the exponential being bounded above, which is equivalent to what the exponential is. So it's like the power is f plus epsilon psi minus lambda phi being bounded above. So we're not quite done yet because we're trying to bound f and phi both above and below. But using the Holder continuity or even just a uniform continuity of the complex Monge-Ampere equation for Hermitian metrics proved by Denevin, Kolij, and Blotsky in this specific non-Keller setting, it follows from this that psi and phi are both uniformly bounded. So that gives us upper bounds on, so phi is already bounded from the statement. This proof gives us the upper bound on F. Then the last thing we need to show is a lower bound on F. And so the lower bound on F, you can in fact prove much more simply than this upper bound on F. And this one follows by just a very simple regular maximum principle argument, where it'll also depend on I of F because the dependence gets passed over in the way that the work unfolds. Okay. And then we have 3 more steps left that maybe you want me to continue. I don't know how long your seminar runs for. I wasn't actually told.
Other people wish, I mean, in the audience. But I think it's going to be very involved, right? In the higher order estimates.
Yeah, the punchline is like the red terms are bad torsion terms. All of the work reduces to controlling these torsion terms, right? Using, I know, Holder and Young's inequalities, and then basically juggling quantities and choosing the quantity to which you apply the maximum principle very, very specifically. Yes. So maybe
yes, that's very involved. Yes.
Yeah.
I think it's better not to enter the details. Okay, so thank you very much. But are there questions or remarks?
I have a question. Hey, Sisi. So you mentioned that you need this condition that dd bar and of the metric and dd bar of the metric squared needs to be 0 for this kind of these things to work.
Yeah.
So aside from Keller metrics and Bott-Chern metrics on surfaces, are there other known examples of metrics like this?
Yeah, it's not really clear. I spent a lot of time trying to for instance, like a complex dimension 3 manifold that's strictly non-Keller and not a product manifold. I couldn't really find any exact examples. Yeah, but in the complex surfaces setting, you know that they exist because the Bott-Chern thing. But also, like a nice example would be like the round metric on the Hopf surface is both constant Chern scalar curvature and Bott-Chern simultaneously. So it's maybe one sort of interesting example. Yeah.
Thanks.
Actually, I had a similar question to Michael. So I was wondering if there is a relationship between these types of metrics and strongly Bott-Chern metrics or balanced metric, that appear in the compact Hermitian case.
I think they're all generalizations of the Keller condition that are weaker than the Keller condition. So the balanced one behaves very differently because that's having closeness on n-1 power of your metric omega, right? So then if you're trying to ask like the question of like existence of constant Chern scalar curvature within the balanced class of a metric, then you're working with like omega n-1 forms, right? Or like things of like n-1, n-1 forms. And I think like to study Weinkow, there is a result out there that shows some sort of analog of proving these things, but then you're working in a very different setting. Yeah. Or I think then by like Poincare duality, you can work with the 1-1 forms, but like a very different type of 1-1 form, I think. Yeah. So I think they're all sort of different from each other still.
Okay, are there extra questions or remarks from the audience? Actually, I have one other question is when they want the result of Tossati, Weinkow, and Cherrier is produced using the Monge-Ampere equation, but they are not using a flow, right?
No, it's just the
so could you attempt to do also a proof of the result using pendant of the Chern-Ricci flow? I mean, would it make sense to do that? Is it done maybe already?
Yes, I think Ben's previous student, Matt Gill, did some work on the convergence of the Chern-Ricci flow in the case of vanishing for a Bott-Chern class. So then all those fixed points are going to give you, I think there is like the same way that you can prove existence of Keller Einstein in those nice cases using the Keller-Ricci flow. I think those analogs also have been shown for the Chern-Ricci flow in the case of vanishing for a Bott-Chern class. Yeah. Well, less is known for the Chern-Ricci flow. For like, so you can assume signedness without being Keller, Like you can assume first vanishing first Bott-Chern class. You can't assume like positive first Bott-Chern class without it being Keller, or a negative first Bott-Chern class without it being Keller. So I think the Chern-Ricci flow outside of that setting, less is known there. Like, unless I expect it to work nicely in that broader setting.
While the flow you are studying, I mean, it's not defined in other settings, right? And but I imagine you have been working on that. No, you have been trying to
I've been
extend
really
it.
doing a lot of integration by parts involving the Mambush energy, like in the more general setting, but it is much more complicated and hasn't worked out for me yet.
Okay, very good. So I think it's time to thank the speaker. She should be, for her very nice talk. So let's do it at least virtually, if not in reality.